A 100 milliliter sample of oxygen gas is collected over water at a pressure of 750 torr and a temperature of 25 degrees Celsius. The vapor pressure of the water at 25 degrees Celsius is 23.8 torr. A. Calculate the partial pressure of the oxygen gas in the sample. B. Calculate the number of moles of oxygen gas collected. And C. Calculate the mole fraction of oxygen gas in the sample. So in this problem, we are collecting gas over water. Now, this is also called collecting gas by water displacement. The whole reason that we do this is because if you want to collect a gas from a reaction, so for example, we are creating some sort of reaction that's producing oxygen gas in this case. So the oxygen gas is being produced over here. It goes through the tube and it bubbles up through the water. And this collection tube here, this test tube, would have been initially completely full of water. And as the gas bubbles up, it displaces the water. It pushes the water down out the bottom. And the gas that's being collected up here is now only O2 and H2O. Now, the reason that we do this is because if we just had an empty tube, well, the empty tube isn't really empty. It's full of air. And so there would be a whole bunch of other things in there. There would be nitrogen and oxygen that we don't want, oxygen that didn't come from the reaction, and argon and whatever else is in the air. And so when we collect it this way, we know that there are only two gases in there. The water is just a byproduct of the fact that water evaporates. And so over the surface of any water, there is going to be a certain pressure that is created by water molecules that have escaped. And so what we have to do when we are calculating the pressure of oxygen is we have to take into account that the total pressure is the sum of the partial pressure of the oxygen and the partial pressure of the water. Now, a lot of AP chemistry gas laws questions start with this type of setup. They will say either a gas is collected over water, or they will say a gas is collected using water displacement. And when you hear those terms, you have to first subtract the vapor pressure of the water that is part of this gas mixture. We're going to do that in part A. Just a little bit of important vocabulary. When we collect a gas over water, the total sample is normally referred to as the wet gas. In other words, it is the gas you are trying to collect that is mixed with the water vapor coming off the surface of the water. And when you are referring to just the gas that you are trying to collect, in this case oxygen, and you are subtracting the pressure that is created by the water, you normally call that the dry gas. Okay, so for part A, it says calculate the partial pressure of the oxygen gas in the sample. So we have collected a mixture of gases, and anytime you have a mixture of gases, you can use Dalton's law of partial pressures, which says, in this case, that the total pressure of the gas is equal to the partial pressure of the oxygen gas plus the partial pressure of the water vapor. That's the only two things in the mixture. And so we want to solve for the partial pressure of oxygen, which means let's rearrange our equation. The partial pressure of the oxygen gas is going to be equal to the total pressure minus the partial pressure of the water vapor. And we know the total pressure is 750 torr. And we know that the partial pressure of water at this temperature is 23.8. And that will change at different temperatures because at higher temperatures, the water pressure increases, and at lower temperatures it will decrease, but at this temperature it's 23.8 degrees. And so if we do this simple subtraction, we end up with 726.2 torr, and to the correct significant figures, which would be to the ones place, 726 torr. And we call this the pressure of the dry gas, or the pressure of just the oxygen alone. Part B, calculate the number of moles of oxygen gas collected. So to do this, we are going to use the ideal gas law. PV equals N RT. We are trying to find the number of moles of oxygen, so we are going to use the partial pressure of oxygen that we calculated in part A. So we'll start with that. 726.2 torr. The volume of the gas needs to be in liters because R is going to be in liters. So I'm just going to divide 100 milliliters by 1,000, and that is 0.100 liters. N is what we want to solve for. R is 62.36 liter torr per mole Kelvin, because my pressure is in torr. And the Kelvin temperature is going to be 298. Solve for N, and what we end up with is 0.00391 moles of oxygen. Part C, calculate the mole fraction of oxygen gas in the sample. There are two ways we could do this. The first way is to use our mole fraction equation that says that the moles of oxygen gas divided by the total number of moles, which would be the moles of oxygen plus moles of water. We could do it this way. However, to solve for NH2O, we would have to use the ideal gas law. And that would take some time. It would give us the same answer, but we're not going to do it that way. We're actually going to do this an easier way. The easier way to do this is to use this equation. The partial pressure of the oxygen gas is equal to the mole fraction of oxygen gas times the total pressure. And you can use this for any gas in a mixture. The partial pressure of that gas will be the mole fraction of that gas times the total pressure. So we already know two pieces of the puzzle here. We solved for the partial pressure of oxygen gas in part A. That was 726.2 torr. We want to solve for the mole fraction of oxygen times the total pressure, which was 750 torr. And now we simply solve for the mole fraction of oxygen, which is 0.968. Which means that another way to think about this is that 96.8% of all of the molecules are oxygen molecules, and then the remainder are water molecules. Or another way to think about this is that 96.8% of the total pressure in the sample is being caused by oxygen, and the remainder is being caused by water. Mole fraction has a tendency to confuse kids. It's actually a really simple concept. It's just a percentage written in decimal form.